VC Chemistry, Unit 4, High Resolution HNMR. In this video, we will focus on how do we use high-resolution proton NMR to identify the structure of a simple organic compound, specifically using splitting patterns and applying the N+1 rule. Splitting patterns. Are you a singlet or doublet or triplet? Well, it's not really like that. Okay. So when we first introduced NMR, we talked about that the neighboring atoms or groups of the nucleus in question will affect how that nucleus interacts with radio waves under that magnetic field. Right? So for hydrogens, the neighboring hydrogens will also affect each other, of course. But interestingly, they affect each other in a very specific way, creating an observable pattern. That is, the peak will split into either a triplet or quartet and singlet, or sometimes even more, based on how many hydrogens are there. Okay. So it works for hydrogens up to 3 bonds away. So the effect is limited. If you're too far away, you don't really affect the hydrogen we're actually looking at. But if there is a neighboring hydrogen that is 3 bonds away, basically most likely is connected to a neighboring carbon, then it will cause a particular peak to split into different smaller peaks. So how do they actually split then? Well, the number of lines that a peak split into is corresponded to the number of hydrogens in the neighboring environment, then +1. Hence the N+1 rule. So, for example, this peak created by the hydrogens on the CH3 group is splitting into 3, into a triplet. So we know that in the neighboring environment of these 3 hydrogens, there will be 2 other hydrogens in a different but neighboring environment. Similarly, this quartet is produced by 3 other hydrogens in a neighboring environment of these 2 hydrogens. And those 3 hydrogens are in a different environment than this guy. So let's look closer. So now we are very familiar with identifying hydrogen environments. So we know that these 3 orange hydrogens are in the same environment. Therefore, they will produce one peak on the spectra, and that peak is not, and they will not cause each other to split. So if you're in the same environment, you produce the same peak, that peak is not just going to split. But these 2 blue hydrogens on the neighboring carbon will then cause the peak produced by these orange hydrogens to split into 2 + 1, 3 small peaks, like that, a triplet. Okay? So are these really neighboring hydrogens? Well, if you count it, there is a CH bond, the first bond, carbon-carbon second bond, and then this CH bond, third bond. So both blue hydrogens are 3 bonds away from these orange ones. Similarly, you would guess that these orange ones will also cause the blue ones to split. Exactly. So since the blue ones are in the neighboring environment of these 3 orange ones, then these 3 will cause the blue peak, or the peak produced by the blue hydrogens, to split into 3 + 1, that is 4. Then your question is, wait, isn't this green hydrogen also in the neighboring environment of these 2 blue hydrogens? Let's count. 1, 2, 3. It is. Well, however, something that we must remember is that this green hydrogen and these 2 blue hydrogens are on 2 sides of this oxygen atom. Oxygen is very electronegative, so the electrons, especially the lone pairs on this oxygen, will sort of act as a shield in between these 2 neighbors. Okay? So because of this shielding effect, the neighbors no longer affect each other. So these two blue hydrogens will not cause the green hydrogen to split, nor will this green hydrogen cause the blue hydrogens to split. So as a result, these two blue hydrogens are only affected by the 3 orange ones and splitting into a quartet, and these green hydrogens will only produce a singlet as a result. Okay, so hydrogens right next to a oxygen atoms will not split or causing splitting. So overall, the neighboring hydrogen must be in a different environment to the peak itself so as to cause splitting. Let's look at more examples. This molecule, we know that these 3 hydrogens will produce a peak, and they are in the same environment, so it's a one peak. However, the peak will be a singlet because they don't really have a neighboring hydrogen. You'll be like, wait, 1, 2, 3 bonds away. There are neighboring hydrogen, but there is also a bond between the hydrogen and the carbon. So hydrogen-carbon, that's the first bond, and then carbon-carbon, second bond. And if you count in that way, this hydrogen here is not really in a neighboring environment anymore. It's too far away, so it doesn't really have an effect on this singlet peak it produces. But these 6 hydrogens, and this one is in a neighboring environment because they are actually hydrogens connected to 2 neighboring carbons. So as a result, these 6 hydrogens, they are in the same environment. They are equivalent hydrogens, but they will split into 2. It will produce a doublet because of the existence of this guy. And this hydrogen, on the other hand, will then split into 7 because of the existence of 6 hydrogens in this neighboring environment. In this molecule, again, it's a similar situation than this part of the molecule here. This hydrogen will cause the peak produced by the 3 hydrogens to split into 2, becomes a doublet, and this hydrogen, the peak produced by this hydrogen, will split into a quartet. Okay. Well, the good news is that the manual for using low-res HNMR still works for high-res. We just need to add 2 extra steps. Okay? So first of all, we still need to identify or determine the molecular formula. We also need to write down all possible structures for that particular molecule. And bear in mind that when we write down possible structures, that's already informed by an infrared radiation spectra, so that we already identified possible functional groups. So that narrows down structures to just the structures on the hydrocarbon chain. Okay? Then we can use HNMR to narrow down the particular environment for the hydrocarbon chain using the number of hydrogen environments produced by the spectra. Then compare it, narrow down some possible structures. If we can't, up until step 4, if we can't really pinpoint one particular hydrocarbon chain structure, then we can use the splitting pattern produced by high-res HNMR to determine exactly which one is it. And last, we can use chemical shift to confirm our deduction. So chemical shift is produced by data book, but we don't normally start with it. We actually finish up with it, using it to confirm our decision. An example, an alkane with molecular formula of C4H10, and the HNMR is produced below. Well, it's just an alkane. You already know it's an alkane, and there are really not many of chain structures we can come up with, right? So let's try the menu out. First of all, molecular formula, it's given. Then, based on the variations of C4H10 and identifying the number of hydrogen environments, so I merged step 2 and 3 together. So the versions that we write for C4H10 should only have 2 hydrogen environments here, because there are only 2 peaks in addition to the reference peak, which is CMS. Okay. Well, two hydrogen environments, the only way that you can write is these two. Butane, because of symmetrical nature, will only have two hydrogen environments because these two are going to produce the same peak, and the 6 hydrogens on the sides will produce the same peak. On the other hand, we can also have a methylpropane, also C4H10, but also has two environments. One is produced by this hydrogen alone, and then the other one is produced by the other 9 hydrogens on each of the 3 CH3 group. Then both compounds have two hydrogen environments, which is confirmed by the spectrum. Then what do we do? This is where we need to use the splitting pattern. So the first peak here is split into 3 in a high-res HNMR. So there must be 2 hydrogens in the neighboring carbons for the neighboring carbon as the neighboring to the hydrogens that produce this peak. And also it's quite high, which means most hydrogens are actually in this environment that is next to the 2 hydrogens, right? And the second peak is split into 7, which means there must be 6 hydrogens on a neighboring carbon, or carbons, right? So look at these two structures we have written down. If it's a butane, then we do know these 4 hydrogens produce a single peak, and that peak is going to split into 7 due to 1, 2, 3. That's 3 bonds away to these 2, and these 3 are also 3 bonds away to these 2. So overall, you have 6 hydrogens in the neighboring environment overall of these 4 hydrogens. So they will split into 7. And let's look at the rest of these 6 hydrogens. These 6 hydrogens will only split into 3. You'd be like, wait, but there are 4 hydrogens in the neighboring environment. But if you look at these 3 hydrogens, the only thing that will affect the peak is these 2 grains. And similarly happening here. So although overall there are 4 hydrogens in the overall neighboring environment, but what's actually going to affect the peak is the 2 here and 2 here. So each time there are only 2 hydrogens in the neighboring environment. These 2 hydrogens will not affect the peak produced by these 3, and vice versa. So the other peak will only split into 3 due to 2 neighboring hydrogens. On the other hand, if it's a methylpropane, one of the peak will have to split into 10 that is produced by this hydrogen, because all of these 9 hydrogens are in the same environment neighboring to this hydrogen. And the other peak produced by these 9 hydrogens will be really tall and only split into 2. So there you got it. It should be a butane that produced this graph. Then in the end, we can use the chemical shift to confirm our deduction. So our data book gives us the chemical shift, and it does sort of like in a similar position. But you can see that although the chemical shift seems to be really specific, 1.3 and 1.4, but in a lot of cases, the high-res HNMR or low-res HNMR given is not that specific when it comes to the number scale. Okay? So we don't usually use chemical shift to determine the structure, but more often we use it to confirm our structure. Okay, and sometimes the range of peak, the range of the chemical shift that the peak will appear can vary considerably under different conditions. So the range is simply too large to be useful for us. And there you got it. 6 steps using splitting pattern to inform the structure under high-res HNMR.